Well, welcome everyone. This is a special session, part of the Ontolog Forum. And the topic today is a new language, KGSQL, which stands for a Knowledge Graph System Query Language. So Knowledge Graph System Query Language. So what I'm going to be talking about today is first to talk a little bit about knowledge graphs. I imagine most of you know about them. Then I'm going to give a formal definition of what a knowledge graph is, which is going to be important for this language. And then I'm going to discuss some issues with the resource description framework, which has been typically used for querying knowledge graphs to the point where it's not unusual to see definitions of knowledge graph that basically say it's an RDF graph. But as I'm going to point out, there are some issues with using RDF as a language for knowledge graphs. So I'm going to introduce then a new language, KGSQL, talk a little bit about it, to some extent giving a little primer on it, and also discussing how it can deal with the issues that I raised. Then I'm going to talk about some implementation issues, some ways in which KGSQL can be efficiently implemented, and then with a conclusion. So we do have a chat room. So if you want to ask questions, please put your comments and questions in the chat room, and I'll try to address them as we proceed or after I finish talking. So about knowledge graphs. They have emerged as a kind of a lightweight semantic network. They're based on this mathematical structure called a graph. Now, none of this is particularly new, but it's fairly recent that we've encountered massively large data sets, and the knowledge graphs have been used quite effectively for these data sets. They're critical for a number of important applications such as intelligent virtual assistants and many others. It's now a popular research area and represents a rapidly growing industry. But what is it? The fact is that there have been many definitions of the knowledge graph in the literature. They're not particularly compatible with each other, although they have a lot of common features. Most of them presume that a knowledge graph would be implemented using RDF. Now, in the Ontology Summit 2020, the theme was knowledge graphs. It examined this problem of the definition of knowledge graph, and the community came to the following consensus, which was published in the communique, which appeared in the journal Applied Ontology. So it's a representation of a set of statements in the form of node and edge labeled directed multigraph, allowing multiple heterogeneous edges for the same nodes. A collection of definitional statements specifying the meaning of the knowledge graph's labels is called its schema. So what is the definition, the formal mathematical definition of this directed multigraph? Well, it's given there. For those who have a mathematical background, hopefully I won't need to be able to explain, I don't need to have to explain this. But I would like to point out there's a critical final part to it, namely that the nodes and edge sets need not be disjoint. So edges can be nodes. So what is RDF? RDF describes resources. And these resources can have properties, relationships between resources, and the resources are identified by a namespace and a name. Now, a database or an RDF graph consists of statements. A statement is a subject, verb, and object, and they sometimes refer to them as triples because of the three parts. The subjects are resources, which can be global or local. The verbs are properties or relationships, and objects can be resources or typed literals. A local resource is also called a blank node. I won't say too much more about that, other than just to say it's basically a resource which is meaningful only within particular graphs, so it's local. RDF type is an example of a resource that's name type in the RDF namespace. And notice that the prefix, like Fred here, can be a blank, empty name. So type in this case is a property. So as I mentioned before, it's most commonly implemented with RDF, but there are some mismatches. In particular, I'm going to talk about higher order relations, literals, context and provenance, and also annotations. Okay, so RDF and knowledge graphs are both based on binary relations, which seems to make them a good fit. Relations with higher arity therefore must be synthesized. So records, ternary relations. So I'm going to give an example now of a classical database, suppliers and parts, that illustrates the issue that one has with using RDF. So this is the database, classic database written in SQL. And it shows the three tables, supplier, part, and the relationship between them, shipment. And it gives an example of a record of each of the three types, three tables. Now in RDF, each supplier record is represented by a resource. So its primary key in effect is mapped to this unique namespace and name. And a statement then specifies each of the non-primary attribute values. So QRST is the name of this supplier. And part records are represented in a similar manner. So far, so good. Doesn't seem to be any problem with using RDF for this. But now let's take a look at shipment, the shipment table. This is a many-to-many binary relationship between supplier and part. And you can represent that using an RDF statement, giving the supplier the relationship name, shipment, and then the part. But we cannot add the quantity attribute to this statement. So we're going to need a different strategy. In order to do this in RDF, you have to reify the statement in some way. Okay, this is one way. There are other ways. In this case, what we're doing is using the standard reification notion in RDF, where shipment is reified as a statement, RDF statement, and it has a subject and predicate corresponding to the subject and predicate of the statement that joins these two. But now, because shipment is a resource, we can then give it a quantity. Okay, we can specify the quantity associated with this shipment. So now we can take care of this problem of not being able to associate the quantity to a shipment. But it has some problems. Of course, as you can see, it's inefficient. The single statement now becomes 4 statements. It's awkward. Queries are now much more complicated. So you have to navigate through all of these additional properties. It's inconsistent in a subtle way because there's no connection between the unreified statement and the reified statement. So if in your graph, your knowledge graph now, sometimes it's reified and sometimes it's not, you're going to have to deal with this in a much more complicated query. It's also inflexible. Adding an attribute can be very complicated and error prone. You now have to introduce a reification. Compare this with how simple it is to do that in a relational database. So what about literals? That's another issue with RDF. Since literals are not resources, one cannot specify properties that literals can have, such as measurement units. So again, you need to reify in order to be able to attach this additional property of the unit. And one of the ways that this can be done is to use this standard notion of a compound literal. But it's by no means the only way that you can solve this problem. In any case, however you solve it, it still has many of the same problems as with higher order relations. You need to do some kind of reification. Context and provenance are another example where we have to do reification in order to deal with the kinds of things we would like to do with knowledge graphs. Now, in this case, the issue is that statements are not meaningful in themselves. You generally need to be able to specify semantics and pragmatics of collections of statements. So it's the provenance of the whole collection that's important, not just provenance of individual statements. And of course, you need to be able to specify things like context as well. In order to represent this in RDF, you need to be able to specify that an RDF statement belongs to a collection. And they have that feature. It's called a named graph. So the name of a graph then can be regarded as the reification of this collection. But it has an interesting consequence. In practice, in an RDF data store, you have to actually have 4 parts for each of your statements: the subject, the verb, the object, and the name of the graph. So RDF statements are actually quads, not triples. Many other examples of kinds of attributes, annotations, I should say, that we would like to add to statements and collections of statements are kinds of annotations such as uncertainty, risk, trust, and it goes on and on. These are all important, but you really need reifications in order to be able to annotate with all this additional information. So you begin to see the theme that's emerging here. We need reifications. We need them a lot. It would help to be more systematic about them and perhaps more efficient, and to be able to handle them in your queries. So to deal with this, I introduced a language that I called the Knowledge Graph System Query Language. I want to thank Janet Singer for suggesting this name for the language. It's not just another query language, I should point out. It has features that go beyond RDF. And it's really designed for general knowledge representation. It's based on this definition of a knowledge graph. RDF, of course, when it was developed, didn't have such a definition to be able to base itself on, and for query languages to be based on it. So you can understand that they would not support these kinds of things. But the basic idea that I had, at least initially, was to have E actually be a subset of E. In other words, every edge be reified. And to do that just automatically. However, I'm going to explain a little later, there are some exceptions. You don't reify everything. But it's relatively minor. Furthermore, in KGSQL, we also, I'll be explaining later, allow literals to be resources so that they can be annotated. Another important aspect is that the statement at reification are the same. You no longer have the split between the reification and the statement. So anyway, let me go on and show you a little bit about this language. Now, an important addition to the language is the concept of a bracket pair. In KGSQL, the notation bracket BC means that B has type C. Okay, that generalizes the notion of this from RDF. So if B is a resource and C is a class, then of course it means the same thing. However, if ID is a statement identifier, and now statements have identifiers because they're reified, the bracket notation tells you which property the statement belongs to. So statements can now be regarded as instances of properties. Properties are a kind of class in KGSQL. So the distinction between property and class starts to disappear in this language. If L is a literal, then this bracket notation indicates what type the literal has. In RDF, you have to have a separate notation to specify this. This double caret notation tells you the data type of a literal, which is necessary because in RDF, it's not actually possible to specify a literal as the subject of a statement. But in KGSQL, that restriction is removed. Now in KGSQL, we have a number of commands. Right? It's more than just a query language, it's also a manipulation language. We can actually manipulate data manipulation. We can manipulate the knowledge graph. So we can insert new statements into the graph, new edges into the graph, if you wish, and we can delete edges. So each of these notions is available. But the most important one, of course, is the query notion. That's the select command. But there's also, we can also use construct. Okay, what construct does is it's similar to select, except that it actually constructs new statements and returns a graph, a knowledge graph. Other than that, select and construct are the same thing. So here's an example of a delete command. So you want to delete a particular edge, or in fact, all edges that satisfy a certain condition. The condition consists of a number of patterns. So we have a pattern that specifies a statement here, and a pattern that specifies another statement. And these patterns have in common a variable that represents the identifier of this first statement. this statement then has a property, namely the probability. And you can also specify constraints. So in this case, what we're doing is deleting all statements that specify that a person is named Fred with probability at most 90%. So the overall syntax of the various commands is given here. So select selects a list of variables, and it will return then all ways that those variables can be instantiated. So it's in effect returning a table or relation. Construct is like select, but it returns a graph. Insert, same as construct, except that the constructed statements are now added to the database. Delete deletes the statements that are identified by the variables in the list. So syntactically, delete and select look the same, except that in select you can have any variable. In delete you can only have variables that represent statement identifiers. And much like Sparkle and KGSQL has borrowed a number of constructs from Sparkle, you precede each of these by a definitions of the prefixes that are to be used in the patterns. Okay, so how does this resolve these RDF issues that I raised? So what I'm going to do in the next few slides is explain how it resolves these issues. And in addition, I'm going to show some other new features that KGSQL has that go beyond anything that you might have in RDF. So first, there's higher order relations. All right, so unlike RDF, statements are automatically reified. So you can just automatically refer to their identifier, and you can proceed to add attributes. So in this regard, it looks like a concept known as a property graph. In any case, queries involving this knowledge graph here, the supplier part case, are then going to be much simpler because we don't have to explicitly reify the statement, or excuse me, the shipment. Now, a nice way you can visualize this is given in this little picture here, where we have a property that's linked directly to, right out into the middle of this edge here. So edges now are resources, and as a result, they can be subjects of statements or objects of statements. However, in many ways, the supplier and parts database is unrealistic. Since there's only one quantity for each supplier part pair, and the customer is not specified. But this particular example was given only to illustrate a point, not to be a realistic database for any application. But if you did want to add additional features, well, that's no problem. You could have a sold to relationship, and you could have dates and quantities. But even this isn't quite accurate. It's not very realistic. What you really want is something like an invoice. So we want a relationship between the supplier and the customer. And the invoice then represents some sale that occurred on a particular date. And it has items that are part of the sale, and each item has quantity, and you can have other attributes as well, such as costs related to the different parts, and so on. So what you see here is actually that the knowledge graph starts to look like a tree structure. So we can start representing trees in a natural way in this framework. So what are the advantages of taking this approach? Well, okay, now it's efficient. We don't need those extra statements. It's convenient. Queries are much simpler. Consistent. The unreified statement and the reified statement are the same. We never have to worry about partial reification. And if you put constraints on your shipment statements, they're going to be imposed on the reifications. That's not something that's true for RDF. For RDF, if you want to put, say, an OWL, use an OWL constraint, you have to constrain both the reification and the property. And you can't actually do that with just RDFS, by the way. You need something more powerful like OWL to be able to constrain reified statements. And these constraints start to look kind of complicated. It has more flexibility. I mean, it's really easy to add attributes. And relational and hierarchical models now can be specified much more easily in this graph framework. So what about literals? As I mentioned, literals can be given properties because every literal has a data type. And so it has this statement, namely the statement that the literal is has a type that's a particular data type. So here, for example, 887 is a type decimal. And so that statement has is reified. It has an identifier, and that identifier can then be used to specify the unit. Okay, and then you can specify that a part weighs a certain amount by just linking the part to this reified statement. Similarly, for other issues like context, provenance, and other annotations, you can make use of this reifications. There are actually two possibilities for how one could talk about to specify collections of statements. One of them is just to take a particular subject, one particular subject, one particular resource, and a particular property, and then say that your statement, your collection, is just all of the statements that are the objects of this subject via the verb. And that was actually considered as a possibility for named graphs in RDF. But it was rejected for kind of obvious reasons, that you'd have to reify all of the statements in order to be able to do this. And it was just, they decided that, well, that's just much too inefficient. So instead, what they did was to specify that, specify this notion of a named graph. Now, each of these notions of named graph, and I've just specified here, are are possibilities now in KGSQL. The reason for this, and for the reason why it might be useful to do both, is that each one has its advantages and disadvantages. The second one is efficient, but it has a disadvantage that a statement can only be in one named graph. So you're kind of limited in that regard. Named graphs are then disjoint. If you wanted to regularly deal with overlapping collections of statements, the first one would be more appropriate. But both of them can be done quite easily in KGSQL, because in KGSQL, essentially all statements are reified. Well, okay, and another interesting point, this is not really it's something of an issue in RDF, and that's linked lists. There is a mechanism for defining a linked list in RDF. So I give an example there of a linked list linking 3 people, Ken, Greer, and Ching. And I show how this is specified in with statements in RDF. A, B, and C here are local resources. So that looks good. It is, in fact, used a lot in RDF. But you could also do it in KGSQL much more efficiently. Namely, link via the reifications. So you go from statement to statement, and you'll notice that the picture that you have over here on the right is the motivation for the logo that I created for KGSQL. It appears up on the right, upper right. The KGSQL notation for this is actually an extension of the bracket notation. You specify your linked list, and then you indicate the property, which is the one that is used as the property of the statements in your linked list. But you could just leave this out, and the default property for a linked list would then be used. So in KGSQL, as you can now see, a linked list, this linked list notion has some advantages. It only requires one built-in resource, requires half as many statements. You still need a nil notion, of course, because empty lists have to be represented. And but it has this nice feature that any property can be used for linking, provided that this property has compatible domain and range, of course. And actually, that's an interesting advantage of KGSQL, in that there isn't any really easy way to specify the domain and range. You know, what elements can be in a linked list in RDF. Many RDF tools don't allow you to do this at all. But even if you do, try to do it, it's kind of complicated to do that kind of specification. But there's no problem here in KGSQL. So you can have linked lists of a particular type. Retrieval of a linked list can be done as I'm going to show in the next slide. And linked lists are circular, So if one requests an element, you go beyond the end, then you go beyond, you'll go into the around the list again. So the way that you retrieve is you use multiplicities. Multiplicities are specified with the pattern that I've shown here, from a minimum to a maximum. And there are two ways to iterate. You can either go from object to object, okay, as pictorially shown on the right here, or you can go from statement to statement, which is what you would do with the KGSQL linked list. So you just specify how many edges to follow, and then it'll give you this result. Notice how the statement here looks rather similar to the way you do array selection in a programming language. One difference, of course, is that in KGSQL, there can be many solutions to this, whereas in programming language, at least each time you execute it, it's only one. But of course, you can execute it many times, so you then get roughly the same effect as what happens in KGSQL. And in fact, in KGSQL, you can have negative multiplicities. So you can go backwards through your list. So that's another nice feature. And in general, of course, a pattern that I've shown you a number of examples of already is given in a manner similar to Sparkle, but except that you can add bracket pairs and multiplicities. Another feature that I added is that you can specify type unions. So in other words, if you wanted to specify that the variable there could be either a person or a company, then you could specify it with the this pipe symbol in the bracket notation. This can be convenient, especially when you're using something like a linked list, where you might want to have several different properties that you traverse during the linked list, or if you wanted to make sure that you include the case nil. So what about implementation? Of course, that could certainly be an issue. What good is a new language if implementing it is going to be, just completely infeasible? And in fact, if you did use RDF reification, it would be quite inefficient, especially when you consider that you can, in our KGSQL, you can reify reifications to any number of levels. So just imagine trying to reify and reifications endlessly. But the fact is there's an implementation that is both simple and efficient. Remember I mentioned that in an RDF data store, triple store, they're actually based on quads. Now what you can do is use that fourth part to be the statement ID. Roughly speaking, what you're doing is saying that every statement is its own named graph. Well, but this doesn't actually eliminate the possibility of using that last part for specifying named graphs. Namely, what you can do is use the prefix, right, the namespace of that ID to be the name of the named graph. And if you use a tree index on the primary key of the of your knowledge graph, because the statement ID can be thought of as the primary key, then this tree index would just naturally group by these namespaces. So you really do get, you're really not eliminating the possibility of having having named graphs by reusing this last column for a statement ID. But as you can see now, it's actually quite efficient. Every statement uses up exactly the same amount of space as it did before. Okay, now what about now there is a little technicality I thought I'd mention, and that is that a statement is an instance of the property. For example, example given there that Fred has named Fred, the statement has type name. However, it is not actually, we cannot actually assert that this statement has type name, because what happens if you then do this, then you end up getting an infinite series of statements, because that statement, right, then itself has a statement associated with it, namely that it is type, and that one then has type, which then has type, and so on. So rather than have fun with the mathematics of infinite graphs, I thought it might be more appropriate pragmatically just not to have, not to universally, not to have every statement be reified. So don't reify this statement. Okay, so a few other little technicalities, like some of the resources that you have in RDF are no longer necessary. You also have some nice features, such as the ability to use multiplicities. And in a particular implementation, you might actually implement lists as arrays to further improve performance. Something that you might be able to do in RDF, but I'm not sure that RDF linked lists are actually used enough that it would help very much. But if you do start using arrays a great deal, so for example, if you're going to start represent JSON data, then this kind of performance improvement would actually be quite a big win. So so I'm almost finished here. I want to have some time for questions. Going back to the original definition, okay, what is a label? And in a way, that was kind of one of my original motivations when I first started, way back, I think it was last October, when we were developing the communique. I noted that V and E need not be disjoined, and I said, well, what if one is a subset of the other? And the other question was, oh, but also, what are these labels anyway? So there's a natural notion of what this label is for KGSQL, namely it's a bracket pair. So the bracket pairs are the labels. When and in most cases, of course, the bracket pair would just be have a single type, not a type union. So in practice, the label would effectively be just its identifier and type. Now, there are other graph query languages. And I should also mention there are programming languages that have graph capabilities, graph processing features. So there's quite a few of these. As far as I know, they don't essentially uniformly assume that everything is reified. The closest in a query language that I found was RDF star, but that's still based on RDF reification. And it's pretty much just limited to reifying for the purpose of giving properties to relationships. A property graph is a special kind of knowledge graph where the relationships or edges are reified, and the edges can then have properties, but they do not themselves participate in relationships. Properties are not reified. Data type specifications are not reified, as far as I know. So here's the conclusion. So this is a new language, has some useful features, such as supporting non-graph structures such as arrays, trees, and JSON, and even some nice new features for relations. And so it kind of unifies a number of different ways of specifying data. There's the relational model, there's the JSON model, there are hierarchical databases, and there are graph databases. This notation, while it's not a total unification of all of them, certainly goes a long way toward making it much easier to deal with these different ways of representing data in a nice uniform way. And it does it with a pretty efficient implementation with many opportunities for improvements, which is certainly very important when you start representing different kinds of data that traditionally would not be considered appropriate for knowledge graphs.